So chapter 2 is working with units, and we'll essentially use principles of unit analysis to solve the majority of the problems in this chapter. In fact, that's probably almost all the problems that we'll solve in this chapter will be through unit analysis. So the units of a quantity describe what the quantity measures or counts. So in other words, units of feet measures a distance of length, and units of miles are also a measure of length. Gallons measure liquid contents or fluid contents, volume, really, so on and so forth. Seconds measure time. And unit analysis is the process of working with units or analyzing units to help solve problems. So a really nice thing about units is that if they're involved in a problem, you can often use the units of the quantities that you're given and the units of the quantity you're asked to calculate to sort of guide your calculation in the process, to guide your work. So we'll see that in numerous problems in this chapter. So let's get some language covered first. So when we see the word per written in something as in miles per hour, well, we realize that there's an arithmetic operation that happens here. There's some kind of math calculation we do. Miles per hour would literally be the number of miles driven divided by the number of hours that took. Miles per hour. So when we see the word per, we think division, and that will always be the case. Okay, so we'll connect this with the idea of division. That's a rate, is what that tells us. Miles per hour is a rate of change of distance over time, in other words, speed. Okay, as in 3 bags of a dozen apples. Well, if we were to calculate the total number of apples and we had 3 bags of a dozen apples, well, we'd realize that's 3 times 1 dozen. And well, 3 times 12 is 36, right? So this of word will connect with multiplication or times, right? So we can pretty reliably use those interpretations of that language in calculating these problems. A little bit less common in this chapter is area. When we think of area, we think of squaring, right? So squaring is the main idea, and that's something like x squared or square feet or square miles, or quite possibly acres. That's another one that gets thrown in there. It's a measurement in square feet. It's roughly 43 or 44,000 square feet is an acre. Okay, volume, very similar. This is cubing, right? Taking a length x and perhaps taking it to the 3rd power if that volume's a perfect cube, just like for x, if that was the length of a perfect square, to find the volume would just be x squared. But other measurements here, or units for this, would be cubic feet, cubic miles, and so on, right? Similarly. So that is just a little bit of language to get started. Let's see some of our first easier problems. We will be dealing with fractions quite a bit, so it doesn't hurt to just have a quick review of evaluating fractional expressions. So, of course, we've done a little bit of this in past chapters. It certainly doesn't hurt to continue with it. Multiplying fractions is one of the easiest things we can do. So if we have product of 2 fractions, we take the product of the numerator divided by the product of the denominator. Nice thing to review. Note that we could have made a simplification before we started that, but we can also make it in the end. We have 2 over 12, and we realize that this 2 is an even number, 12 is an even number. They have a common factor of 2, so we can cancel that 2 out to get 1 in the numerator and 6 in the denominator. So our overall answer should be 1 over 6. So evaluate and simplify each of these expressions. Okay, adding 2 fractions is a little bit more complicated because we require a common denominator in that situation. So the common denominator in this case, the easiest way to get a common denominator, if we don't see one immediately, is to just take both common denominators, or both denominators, and multiply them together. So we'll do that. It'll be 4 times 3 is 12. So That's a great common denominator to use here. Sometimes they can be more simple than that, but this one will always work. If you just multiply the two together, you'll get the common denominator that you need. So we need a common denominator of 12 for the fraction 1/4. So that's going to tell us that we need 3 times that 4 in the denominator. So we'll write 3 over 3 times our first fraction. Okay, this part is just changing our expression, but without changing its overall value, because this is in fact equal to 1. And multiplying 1/4 by 1 won't change the value of 1/4. But if we write it as 3 over 3, of course it still won't change the value, but it will change the way that the value is represented. Well, I'll make a note about that once we've completed this next step. Now similarly, we have 1 over 3. It needs a common denominator of 12, so we choose to multiply by 4 over 4. Again, this is equal to 1, so it doesn't change our value of 1/3, other than expresses it in a new way, a more useful way. So multiplying each of these fractions here and here, here and here, numerator times numerator, denominator times denominator for all 4 of these positions, we have 3 times 1 over 3 times 4 is 12, plus 1 times 4 is 4, over 3 times 4 is 12. Now we have a common denominator. Once two fractions have a common denominator, their numerators can be added over that common denominator. We don't add the numerators, we just add the denominators, we add the numerators. So the denominator remains as is, and we add the two numerators. This results in 7 over 12. And that's the answer to that one. So again, the reason we multiply by each of these factors of 3 over 3 and 4 over 4 is because that is a form of 1, and all it does is change this fraction of 1/4 to be written in a new way. We know that 3/12 is actually 1/4 if we simplify that fraction. Similarly, we know that 1/3 and 4 over 12 are actually equal to each other as well. If we simplify 4/12, we'll get 1/3. So we're just building them up so that they have matched denominators so we can actually add them. Okay, lastly, dividing two fractions, it's a little bit easier than adding two fractions. And we have 3/5. So a nice expression for this is keep this one, change that sign to a times, and flip this fraction. So keep, change, flip is a reasonable way to think about this. And there we go. We've got exactly what we need for this line. And 3 times 9, we're back to multiplying fractions. It's a nice, easy job. We have 27 over 50, and that simplifies that. So since we will deal with some pretty complicated arithmetic expressions, it doesn't hurt to have a little bit of review of dealing with fractions behind us. So let's get into our first unit problems. So unit conversion. So one of the most standard things we're ever going to do in here is just convert units from one to another. In fact, that'll be the bulk of the problems we do, even with the more word problem type exercises we do as well. So a conversion factor it's essentially an identity, an equation. It's a ratio of two different units, which is equal to 1. Okay, so let's see a conversion factor before we really start trying to talk about what that is. So in the first example, we're asked to form the different conversion factors for the fact that 8,280 feet equals 1 mile. We're also asked to convert 2.5 miles to feet. Okay, so a few steps in this exercise, but the first thing we'll do is deal with a conversion factor. So if we have this identity, 5,280 feet equals 1 mile, well, we can divide both sides by 1 mile. If we do that, we'll have 5,280 feet on the left divided by 1 mile, and that's equal to 1 on the right because we divided by 1 mile. So there's one conversion factor. It's a ratio. This is a ratio, a fraction, right, of two different units, right, which is equal to 1, and this is equal to 1. Okay, so all of that is as defined, and we built our first conversion factor. Now, there was no reason we needed to divide by 1 mile in this initial identity right here. We could also divide by 5,280 feet and get another conversion factor. If we do that, on the left, this is starting from up here again, dividing by 5,280 feet. So on the left, we'll have 1, since those are equal to each other. And on the right, we'll have 1 mile divided by 5,280 feet. Both of these equations are a result of this equation. Okay, so but we can use either of these conversion factors to convert one way or the other. This one converts from miles to feet, and converts miles to feet, and the other one does the opposite. This one converts feet to miles. Okay, one thing to notice about these conversion factors that's very useful, just like when we added two fractions that didn't have common denominators, we multiplied by a form of 1, 4 over 4 and 3 over 3. Well, these conversion factors are also forms of 1. So we don't change the quantity we start with in terms of its actual values, but we do change the numbers, the way that it's counted in units. So it's accurately converted from one to the other. And similar here, this is equal to 1, so this conversion factor won't change the actual measurement, it'll just change the units that it's written in. So there's our idea, and there's a connection to the fractions that we just talked about. Now we're asked to convert 2.5 miles to feet. So one of the preferred ways to do that, especially for this class, is to use the stoichiometry table. You don't have to do that. If you become adept at these problems without such a table, that's fine. But when they get complicated, this table can really help you out a lot. So if you're going to use the stoichiometry table, stoichiometry, might not have spelled that right, but I believe I'm close. What you'll start with is the quantity you're given. We're asked to convert 2.5 miles to feet. So you write down what you're given. We're given 2.5 miles, and you'll draw this horizontal bar some distance across the screen, across the page here, and you place your original value over 1. Okay, we're starting with this. We need to convert it to miles. Now this horizontal bar is essentially our fraction division bar. Okay, this vertical bar is a multiplication. So across the vertical bars we'll multiply, across the horizontal bar we'll divide. All right, so maybe I'll leave that arrow there, and this is multiply, and across here is divide. Okay. And this gives us a nice way to lay out all our information and check our calculation before we run it all through. So we need to convert miles to feet. We need our answer ultimately to be in terms of feet. So having our goal in mind will be helpful as well. Well, if we're going to divide 2.5 by something, and this is miles, we need miles to cancel. We can use either this conversion factor or this conversion factor. Well, if we use the conversion factor at the top, this one, well, that will cancel miles. So let's fill it in. You can also just guess one conversion factor or the other, write it into the table, and see whether or not it's going to work. But when I write the first one in, I have the following. And I see that, yeah, in this setup, miles will cancel. Miles will cancel, and we'll be left with feet. That's exactly what we'd like. Had we used the other one, we'd see that miles wouldn't cancel because it would be in the numerator and feet would be in the denominator, and our units would be something like miles cubed or squared over feet, and that just wouldn't make any sense. So that's essentially unit analysis right there guiding us in this problem. If our units don't make any sense, or if they don't match our output, then we haven't done it right. So it's a nice check. Okay, so miles have canceled. We've chosen the right unit conversion factor here. And to complete this, we just multiply 2.5 times 5,280, and that'll give us the result of this. When we plug that into a calculator, the answer we get on the left-hand side is 13,200, and of course that answer's in feet. So I'll go ahead and box this up entirely to match that. We convert it from miles to feet. Good. The next problem. How many seconds are there in a 1.25 hour long class? Okay, so we have 1.25 hours. we're asked to convert it to seconds. So how many seconds are there in 1.25 hours? Again, we're only given 1.25 hours, so we put our measurement with its units down in the top left of our stoichiometry table. This is a stoichiometry table. Fill that in. Now, and then we place that over 1. It's not a rate or anything like that, so we just place it over 1. So we need to convert to seconds. So a conversion factor here that could help us is to convert halfway. We know that there are 60 minutes in 1 hour. These two things are equal to each other, so this is just a form of 1. We're multiplying our original quantity by 1, but it does us the service of canceling hours and leaving us in a measurement of minutes. We're still not quite at seconds, but we can absolutely repeat this. And that's what's nice about this table, is we can do whatever conversions we like on one big, long table. So again, 60 seconds is 1 minute, very similar to what we just did. And this, we set it up like this because we see that the minutes will cancel across the division bar. Now we're left with seconds. That's perfect. That's exactly what we want. So when we total all this up, let's remember that we do 1.25 times, so it's times across the vertical bars, times 60, all divided by 1 times 1 times 1 along the vertical bars in the beneath the division bar, so along the bottom. And this is seconds. And the result of this, once we plug it into a calculator, 1.25 times 60 is 4,500 seconds. Okay. Now, if we were to flip one of these components here, or both, we would come up with an answer that's quite a bit different than this one. And it would be so different that we should be able to notice it. If we know that there are 60 seconds in a minute and there are 60 minutes in an hour, then 1.25 hours should have a whole lot of seconds in it. It shouldn't be a decimal number, smaller than 1. Okay, so if we were to flip it and do this wrong with these conversion factors, this answer would have been a decimal. It would be much smaller than 1. And we'd say, it doesn't seem like there are 0.0004 seconds in 1.25 hours. It seems like there would be at least a few thousand seconds in 1.25 hours. So that's a nice way to check the sense of your answer. Similarly, for the problem above, we started with 2.5 miles. We know that miles is a much longer distance than feet, or 1 mile is much more than 1 foot. So when we're done, 2.5 miles should be more than 5,280 feet. So we'll get somewhere in the thousands. If we were to do this wrong, we'd have some small decimal number, and we'd realize it shouldn't be that 2.5 miles is equal to 0.00 something feet. That would be that should catch our attention when we work on these problems. So always check your answer for cents based on the units you're dealing with. It's another nice thing about working with units and unit analysis. So conversions with units raised to powers. This is just something to be careful of if we talk about area and volume. Okay, so when we will deal with more problems specifically with area and volume, but just to see what they're talking about in this, a point that the book makes and that we should make here is that if there are 3 feet in 1 yard, it's a good question to ask, how many square feet are there in 1 square yard? Okay, 3 feet in 1 yard, how many square feet are there in a square yard? It's very tempting for a student to say there are 3 square feet in 1 square yard, but that's wrong. Why is that wrong? Well, let's look at a picture. If this is 1 yard, this whole length right here, okay, then we can split up that length of 1 yard. This could also be 1 yard along the vertical lines here. I've intentionally drawn a square. So we know that this yard is split up into 3 feet, right? Problem has told us that, or reminded us that there are 3 feet in 1 yard. I'm sorry, this is one of those 3 feet, so we'll label that as 1 foot, and each of the other 2 is 1 foot as well. Well, we can do this also along the vertical axis. There is 1 foot and another foot, And we can label this as 1 foot along this, and the other two are also 1 foot. And what we'd see if we were to dot these lines in and take our time with this, we'd see that if we divided this square yard, which this whole area is 1 square yard, by the way, 1 square yard. The area of a square is, it's the length of its sides times each other. So 1 square yard came from 1 yard times 1 yard, and that's 1 square yard. Okay. So again, coming back to what we're looking at in the pictures, we're dividing this thing up to think about how many square feet are in it. And I think we start to see what the issue is now that this picture is complete. Each one of these spaces is 1 square foot, because this length is 1 foot as well as this length. And to get the area of this square here, we do 1 foot times 1 foot to get 1 square foot. Well, there are 9 of those, so 1 square yard is equal to 9 square feet. So we found this answer via a picture, but what's really happening is this. If we have that, here's our alternate way to calculate this. Alternate calculation, I'll call it. The alternate calculation is to say that 1 yard is equal to 3 feet. And then we want to talk about square yards, so we just square both sides of this equation that we're given. So 1 yard squared and 3 feet also squared. Well, the result of doing this is 1 squared, which is 1, square yards. That's how we denote square yards with that exponent of 2. And 3 squared, which is 9, feet squared, or square feet. And we get exactly the same thing that we asserted above. And so however we get to it is just fine. However you understand it is fine, but in the future probably this will be the faster way to do these instead of having to draw a picture every time. Okay, similarly, below, if we have 1 cubic yard, how many cubic feet are there in 1 cubic yard? Well, it's not 9, it's not 3, something more going on, right? Again, let's think about splitting this, the faces of this square up so that they're in, or this cube that we're given, equidistant, so there are 3 faces there, or 9 faces there actually, and then when we do this on the front face, we realize that what's going on with this cube is that it is split up into 3 layers of 9 blocks. So I'll draw one of these blocks in red. So in the back here, there's this 1 foot by 1 foot by 1 foot block right here that's making up this part, this part of the cube, the 1 cubic yard cube here. So 1 cubic yard, or 1 yard cube. There's 1 there, so that means there are 9 of them here, 9 blocks on the top. There are 3 layers of blocks, 2 and a 3rd layer, right? 3 stacks of blocks, so 3 times 9 gives us 27 cubic feet. Now this might be harder to see, it might be harder to follow, but remember our old trick. Our alternate method will work just as well. We'll remember that 1 yard is equal to 3 feet. Equal to 3 feet. We cube both sides. 1 yard cubed is 3 feet cubed. And we cube everything. We cube the numbers, we cube the units. 1 cubed is 1 cubic yard. 3 cubed is 27 times feet cubed, which is feet cubed, or cubic feet. So our alternate method's a lot nicer for this one, but I think we can imagine the situation that's drawn on this picture to the left as well. So that's it for the first part of chapter 2. The second part has some slightly harder problems. We're going to see things that are essentially word problems that we'll use unit analysis to solve. So be sure to check out that video, as it's going to contain a little bit more difficult information.